Right, let's push on with the stuff we were doing about distance measurement last time. If you remember, method one, if you like, was using angles. All right, very nearby things, and by that we mean things like the moon, the sun, the planets. Measuring angles is a possibility, okay? Using long, thin triangles and sine and cosine and stuff. If you know how big something is, then the angle it gives you will tell you how far away it is, and so on, okay? Moving out from interplanetary distances into interstellar distances, so things that are more than 4.5 light years away. One method you can use is the method of parallax, okay? And we explained that last time, all right? Parallax only works for relatively close by things. If you think of the scale of the Milky Way, parallax is only going to get you some of the nearest things in the Milky Way, okay? Across the galaxy, outside the galaxy, things like that, heliocentric parallax just won't work because the angles, the difference in the positions of objects from one point in the year to 6 months later is going to be so small, or the shift, if you like, is going to be so small that you won't be able to measure it, okay? So if we move on to much more significant interstellar distances, method number 3, a good way to think of it is that you basically use the HR diagram, okay? And we use the HR diagram to determine the absolute magnitude, okay? Now it might be worth just pausing to make sure we're clear about the difference between apparent and absolute magnitude. Capital M, which is absolute magnitude, okay, is obviously related to the actual power output of the star. Okay, I like to think of it as kind of a fair test for star brightness because you imagine measuring it at a distance of 10 parsecs, and we talked about the definition of the parsec last week. Okay, absolute magnitude is the brightness of the star on the magnitude scale, that funny scale with 0 in the middle, negative at the top, plus at the bottom, and timesing by 2.5 every time you go up a step. Where do you feature on that scale, measured at a distance of 10 parsecs? That is called your absolute magnitude, okay? As opposed to your apparent magnitude, which is how bright the star appears from Earth. If you looked at your position on the magnitude scale from Earth, then you're not measuring absolute magnitude, you're measuring little m, which is apparent magnitude, okay? Now, why does the Sun have a really very ho-hum absolute magnitude? It's not a particularly powerful star, and yet has an enormous absolute magnitude, bigger than anything else in the sky by miles. Why is that? Yeah, because the Sun's really close, isn't it? All right. Why does a star like Rigel actually have a huge absolute magnitude? Because it's a tremendously powerful star, and yet the apparent magnitude is, way lower than the Sun. Is obviously because Rigel is a long way away. Okay, so we're thinking there are basically 3 things which are connected here, which is distance, absolute, and apparent magnitude. Okay, those 3 things are clearly connected in a formula, like speed, distance, and time. If you know any 2 of them, you can work out the 3rd one. Okay, unfortunately, just to remind you, the formula is not quite as simple as speed is distance divided by time. The idea is still the same. If you know any 2 of these, you can work out the 3rd. But unfortunately, big M equals little m minus 5 log d over d, where big D is just the standard 10 parsec distance. Okay, big D isn't actually a 4th variable. It's just big D is always 10 parsecs. Okay, so big M, the absolute magnitude, and little m, the apparent magnitude. If I told you both those things, then in theory you can work out the distance of the star. Okay? So if we relate this formula, the distance modulus equation as it's known, if we relate that to what we're doing here, which is measuring distance, what this says is if you know big M, if you know little m, then you can work out the distance of a star. It's not quite as simple as dividing one by the other. You have to use this funny formula with logs in. But basically, that's what this formula is telling us. All right? It's like the eternal triangle of astronomy between absolute, apparent, and distance. If you know any 2, then you can work out the 3rd. So what's the big problem in distance measurement then? That's what the formula will do with us. Think about measuring these two things from Earth, which is where we're always measuring from. If we're always measuring from Earth, what's the problem? What's the practical problem? Apparent magnitude's easy because you just go out in your back garden and measure it. Okay? People have been measuring the apparent magnitude, that's the magnitude as we appear from Earth. People have been measuring those for thousands of years. Okay? That's one reason we have such a nutty system with naught in the middle. Big M's a real problem. How would you know? How would you know that the Sun had a really feeble absolute magnitude? How would you know that Roswell had a huge absolute magnitude? We're never going to go there. We can't send probes there. They're just way too far. And this is the real problem of astronomy then. If you want to measure distance, which is what we're talking about, and as we mentioned last time, is really important because that sets the scale. It enables me to draw these sorts of diagrams and say, that's 100,000 light years, and that's so far from the next galaxy. And basically to set up the structure of the universe is all about measuring distance. Really, really important in astronomy. Measuring distance is discovering things, basically. But the problem is, although apparent magnitude is very easy to measure, absolute magnitude is very difficult. Okay? And we're going to look this afternoon at two methods for getting a handle on absolute magnitude. All right? So it seems like a sort of multi-stage process, but hopefully you can see that if you want to measure distance using the distance modulus equation, then you need to find big M. You need to find a way of working out what the absolute magnitude of the star is. Okay? And that's quite difficult because absolute magnitude, of course, is the magnitude measured from 10 parsecs, and we're not 10 parsecs. Well, I expect there are some stars we're at 10 parsecs from, but from most stars we're not. Okay? And also, just to make sure we haven't got confused on that one, if there is a star in the sky that's 10 parsecs away, why isn't that any easier? Why doesn't that solve the problem for us? Why can't we just look out and say, well, let's pick out the stars that are 10 parsecs away, and then their absolute magnitude is their apparent magnitude? Why can't we actually do that? Yeah, you don't know. Which of the stars are 10 parsecs? No way of knowing, have you? Okay. Right, so this is how it comes down, basically. Distance, we want to know about. Absolute magnitude is the way to find it, and we've got no real way of finding that, okay? The two methods we're going to look at this afternoon allow you basically to get a handle on absolute magnitude, and one is simply to use the HR diagram, which you remember has absolute magnitude up the side against a number of things, but one of the ones you can put along the bottom is spectral class. Okay, most stars live in a band, top left to bottom right, called the main sequence. Okay, now if you think about it, observing from the Earth, as we do, we look at a star, we don't know how far away it is, we don't know its absolute magnitude or anything like that. What you can do, of course, is look at the light from it, and from the light from it you can determine its spectral class. All right. If you remember the funny sentence, WOBAFGKMRNS, yeah, you might look at a star and say, well, actually, we can tell that it's spectral class K4 or something. Yeah, it's 4/10 of the way from spectral class K to the next one. For that, you don't need to know how bright the star is, how bright it is. Is it a bright star a long way away? Is it a dim star close by? Doesn't matter. Because what do you do to find spectral class? Spectral class in simple terms is colour. So you might say, it's a bit more reddish than the Sun. The Sun, as you need to know, is spectral class G2. Okay? And we look at our star and say, well, the light is a bit more red. There's a lot more energy in the red, a bit less in the orange, and so on. And so we put it as spectral class K4. Well, if it's a main sequence star, and you can usually tell that from the spectrum, if it's a main sequence star and it's spectral class K4, then in theory, that would allow you to, most K-type stars are slightly dimmer. There's the Sun at G2, okay, absolute magnitude plus 4, whatever it is. A spectral class of K4, if it's a main sequence star, there's a bit you've got to be tricky about. If it happens to be a red giant or something else, then obviously have a completely different absolute magnitude. But in general, if it's a main sequence star, if you find its spectral class, you're basically comparing it to the Sun. If it's a bit more that way than the Sun, you'd expect it to have a lower absolute magnitude. If it's a bit more this way, you'd expect it to have like that. Okay? So stars like Rigel, we can tell with their spectral class at this end of the sentence, we can estimate their absolute magnitude. Okay? So that's method, the first of these two methods is to use the HR diagram. All right? What can you tell from the light about how bright the star really is? How much of a handle can you get on, is it a dim star close up or a bright star far away? Nothing. But what you can do in really simple terms is to measure the colour. If you measure the colour of the star, that gives you its spectral class. And if you're fairly confident from its spectrum it's a main sequence star, then you can use that to estimate big M, and then you put that into big M equals little m minus 5 log d over d, and that will give you distance, okay? Little m, the apparent magnitude, obviously, you just measure by going outside and looking at it, okay? So this is quite an effective method. It doesn't work for all stars, and it can be a little bit accurate, but basically it gives you a way of estimating the star's absolute magnitude, which you then plug into that formula with the apparent magnitude you measured from your back garden, and you chuck the formula around and you get a value for D. Okay. Now, there is another method for doing this, which is a really powerful method. Okay. Method number 4 on our list is to use stars called Cepheid variables. Okay. Cepheid variable stars have a very unusual property. Okay. And it's this that allows us to measure distance using them. All right. Most of the distances beyond the interstellar that we know about have been measured using things like Cepheid variables. Okay. Cepheid variables have a very strange property that allows us to know their absolute magnitude. Okay. And the clue to this is to do with the fact that they are variable stars. Okay. Which means if you look at their light curve, all variable stars have what's called a light curve. Okay. Obviously level of light against time. There's time there. Light level side. Okay. Cepheid variables have a characteristic shape, sort of a sawtooth thing. They go up quickly and come down slowly. So if you're asked to draw the light curve of a Cepheid variable, don't just draw a wave at the seaside or a sine wave from your maths book. They need to go up quite sharply and come down more gradually. Okay. And Cepheid variables are all over the place. You can look in our galaxy, you can look in other galaxies, and you can find these stars called Cepheid variables. Okay? You draw the light curve, they've got this characteristic shape to them, and their spectra as well give away the fact that they are Cepheid variables. Okay? And what you can then do is to measure their time period, or sometimes just called their period. You can measure the time period. Some are very short, just a few days, some are much longer, okay? And there are Cepheid variables with a whole range of time periods, okay? Short ones, long ones, medium-sized ones. And the amazing thing about this is that their time period is linked to their absolute magnitude, okay? They're quite unique amongst stars. They're variable stars where the time period is linked to their absolute magnitude, okay? Basically small Cepheid variables, which have a fairly small absolute magnitude, okay, they have a very fast, not drawing this very well, they have quite a fast light curve. So they will vary their light output very quickly, okay. If you take another star, which is a Cepheid variable, a much bigger one, okay, they tend to have a light curve which varies much more slowly. So I'm drawing it quite badly. Okay, and there's sort of all points in between. All right. So basically, with a Cepheid variable, a short time period means a small absolute magnitude. Okay, a long time period means a big absolute magnitude. Okay, this connection has a very grand name. It's called the period luminosity law. Okay? Period luminosity law is tremendously useful because it means you can look at a star, it could be a star in another galaxy. Imagine that, you look at this star miles and miles away, it's in a different galaxy to ours, you identify this Cepheid variable star, think about the time period, measuring the time period. It doesn't matter that you're on planet Earth. You could be stood next to the star, watching the brightness going up and down. You could be the other side of the universe, watching the brightness going up and down. What effect will you being a long way away? What will that have on your light levels? Well, your axis up the side, light level, your axis up the side light level, you've got no idea. You don't know. Is it a bright star far away? Is it a dim star close by? You've got no idea. But it doesn't matter, because what you need to measure is the time period. Okay? So that's the good thing about these stars, is what you need to know about them is their time period. And that doesn't matter whether you're close up or far away. No matter what distance away you are, you don't even need to know what distance away you are. You can still get an accurate value for the time period. Okay? And they can be short time periods or long time periods. Okay? But the time period, and you often see the graph drawn like this, basically big M against time period. Okay? The longer the time period, okay, the bigger the absolute magnitude. Okay? And as we've seen, this of course then gives you a way of getting the absolute magnitude. Once you've got that, you just measure the apparent magnitude from your back garden, stuff them into the formula, and out comes the answer for distance. Okay? There's a really good way of remembering this, because you need to remember which way round it is. You don't need to know the exact graph or anything, but you need to know how the period luminosity law works. And the way to remember it, I always think, is to remember dogs. Think of dogs. Think of a very small dog, all right, and a very big dog, and they've both been running about on a hot day, and think of the dogs panting. A little dog, like that, wouldn't it? Whereas the big dog, get it? All right, so think of a little dog, like that, and a big dog, yeah. Larger stars just take slower breaths. That's the sensible way of writing it down, or draw a little dog if you want to. Just like big dogs, when they're panting, breath takes several seconds. Little tiny terrier-like dogs breathe very quickly, breath goes in and out very fast. Have that picture in your head. Think of little dogs, think of big dogs, and you get the right way around. Okay? A fast variable, a fast Cepheid variable that's changing its light level very quickly will have a small absolute magnitude, whereas one that's changing its light level much more slowly will have a bigger absolute magnitude. Why that is to do with the astrophysics of what's going on in the star, some clever stuff with the outer layers, doing all sorts of interesting things, none of which you need to know for GCSE. So that's as much as you need to know today. Okay? But you need to know the process, measure the time period, use the period luminosity law to get the absolute magnitude, and then, combining it with the apparent magnitude, you can use the formula to work it out. Okay? And this is really useful. Somebody once called them like standard candles. When you see a standard Cepheid variable, you know its absolute magnitude. And so if it appears really faint on Earth, you know it must be a really long way away. If it appears quite bright on Earth, you know it must be quite close. It gives you a way of cracking the problem that generally, when you look out at the night sky, which of these three things do you actually know when you look out at the night sky? That one. You can only measure apparent magnitude from Earth. You can't measure distance directly, and unless you've got some other way of doing it, you don't know the absolute magnitude. All you need to do then is to crack this one. And that's what distance measurement in astronomy is all about, is finding cunning ways, using the HR diagram, using the Cepheid variables, period luminosity law, some other way of getting a handle on the absolute magnitude. Because once you've got two of them, as you know from your maths, once you've got two, the rest is just a matter of turning the handle on the equation. Okay? And as I said, it allows you to work out, because think of this Cepheid variable over here in a distant galaxy. If you work out the distance to that star, what have you also worked out? You've also worked out the distance to the whole galaxy. All right? A lot of the stuff we drew in cosmology, we had galaxies drawn, the local group, all that kind of stuff. How do astronomers actually know any of that stuff? It'll be things like Cepheid variables. All right? So a lot of, when you look in astronomy books and pictures of the universe and galaxies and stuff like that, an awful lot of it will have been actually measured using Cepheid variables. Okay, most galaxies seem to have them.